All right, everybody, today's video is going to focus on a new set of angle relationships that we're going to use to solve problems. On the board you have some parallel lines and a line, a transversal that's cutting through them. And then you'll notice I've already pre-numbered them. We have a host of potential angle relationships that form between these groups of angles because these lines are parallel. So the point of this video is to go through what relationships do we have, what does it mean for solving equations, and why this works in the first place. Okay, so enjoy the video. Okay, so let's talk about parallel lines then. What does it mean for two lines to be parallel? If you call back, you know that parallel lines are those that have the same slope. Rise over run, if we're talking about the coordinate grid. Saying that they have the same slope is another way of saying that parallel lines go in the same direction. Well, unlike the intro part of this video, you'll notice I've drawn a couple of lines here that are clearly not parallel. As a matter of fact, they are clearly going to intersect somewhere around here. And the reason I'm doing this is to show you clearly not parallel lines, to examine, well, what properties do these have that we would need parallel lines to be different than? And what I want to focus on here is a couple of angles. If we think of the angles that are created by what would be a transversal is a line that cuts parallel lines. For this case, this is just a line. This line, when it cuts through these two intersecting lines, is creating 8 different angles, kind of like the video's intro. There are 2 groups. This doesn't look the same as the video's intro because we don't have those same relationships that we're going to discuss soon. But let's examine some of these angles. Our goal for parallel lines is for them to be going in the same direction. Well, the only way for us to really measure if they're going in the same direction accurately would be to determine, are the angle degree measures pointing the parallel lines in the same direction? Let's take a look at angle 2 here. I'm going to quickly measure this. Angle 2 is somewhere around 110 degrees, 112 degrees, somewhere around there. So let's call it 110 degrees as an estimate. Okay, this line creating this angle is going, a pretty steep ways there in that direction. It's a very large angle with relation to this transversal. Well, if I were looking at these 2 groups as groups of 4, and I was picking angles in the same position within the group, hopefully logically it would make sense that the angles in the same part of the group would have to be the same if we want them to point in the same direction. This is a gross exaggeration to show you what happens when they're not. Take a look at angle 6, because if we're looking at these as groups of 1, 2, 3, 4, top left, top right, bottom left, bottom right, top left, top right, bottom left, bottom right, 2 and 6 are in that same area, the same position, right? Well, let's take a quick measure of angle 6 with respect to that would-be transversal. It's like about 65 degrees or so, an acute angle. The acute angle, of course, making the line go up. And these are grossly different than each other. And because these angles are so different, they're pointing the lines created by the angle with the transversal in different directions. Because this is an obtuse angle and this is an acute angle, it goes up. Now, what would happen if I were to instead now attempt to create an angle that were 65 degrees with angle 2? Well, I would take my protractor here. I would get it to 65 degrees or so. Right here. That's about close to 65 degrees. Let's just move it up a little bit on my vertex here with this transversal to show you the comparison. And we're about right here or so. Obviously, I'm doing this by hand, so it's not perfect. But take a look at this red line that has a 65 degree angle here now. This is 65 degrees instead of the 110 from before. This is 65 degrees. Clearly, by doing this by hand, I've made a mistake. But take a look at how much closer these lines are to pointing in the same direction. If a computer were doing this more accurately, I'm assuming we could see that these lines would go in the same direction. So what happens and what does it look like when they do go in the same direction? Let's find out. So what you see on the board now is what happens when we pre-measure out these angles, both to be 65 degrees for angles 2 and 6. Because angles 2 and 6 are the same angle measure, these angles are the same measure, related to this transversal, they're pointing this line in the same exact direction. The angles are taking the place of our slope, our rise and run, directing the lines in a certain path. This idea, when you look at the board now, and those of you who are looking at this video, I think many of you would just look at this and realize that 2 and 6 have to be the same for the lines to be parallel. This notion is called a postulate. In mathematics, a postulate is something that is just obvious. It's not a theorem, because theorems come from postulates, but the idea is, and it's not a definition, the idea is this is something that we look at and it's obvious, and then from our postulate that we assume has to be true, because it's so obvious, theorems arise. And the rest of this video, we're going to talk about some other angle relationships that exist because of this postulate. We're going to call these angles corresponding angles. And we're using the word corresponding because these two angles, if you were to overlay the two groups of 4, are in the same positions. All right, so we just discussed what happens when lines are parallel to each other versus what happens when they clearly are not. For lines to be parallel, we know that angles that lie on this transversal between these two sets, certain angles have to be pointing those lines in the same direction, right? So in this instance here, you'll see that these lines telling you are parallel. Certain angle relationships emerge where these angles need to either be equal or they need to fit another criteria just to prove that the lines are going the same way. Parallel lines are lines that you've learned in the past that have the same slope. By showing certain angles here are the same, we're showing that these angles are going in the exact same direction. Okay, so what we just previously discussed, we measured some angles to show that the lines were going in the same direction. Those angles happen to be corresponding angles. Corresponding angles are angles in our two groups formed by a single transversal that lie in the same position. So, for example, angle 1 and angle 5 would be considered corresponding here because they are in the same position in these groups of 4. Imagine picking up this group and overlaying it on top of this one, 1 and 5 would be in the same position. This is the type of angle we measured earlier to show that the lines are going in the same direction. If you remember and you take your protractor and you take a quick measurement of these angles, the fact that these two angles are the same degree measure show us that these two lines are pointing essentially with the same slope, making them parallel to each other. So if angles are corresponding, such as 1 and 5, or such as 2, we'll use 2 markings to differentiate, and 6, 4 and 8, 3 and 7, they have the same exact degree measure. So an equation that stems from this set of angles would be that the measure of angle 1 is equal to the measure of angle 5. Same can be said about the measure of angle 2 and the measure of angle 6, and etc., 4 and 8, 3 and 7. So if you're given a pair of parallel lines, or it's indicated to you that a set of lines are parallel, and a line cuts through them, you can rely on the fact that the angles in the same position have to be the same, and then that relates to some equation solving. Okay, so we just finished talking about corresponding angles and where they're located on our grid here. Because corresponding angles exist, and we discussed earlier when we were proving lines were parallel, that that's a postulate. It's something that's obvious, so additional definitions or theorems or things stem from that postulate being assumed true. We just talked about corresponding angles, angles such as 1 and 5 that we know are congruent to each other, angles 4 and 8, etc. Angles in the same position that have the same measure, they correspond to each other. If you were to overlay the groups, we know that those angles have to be the same if the lines are parallel. It's something that's obvious. Now, a host of other angle relationships build off the fact that we agree that the corresponding angles postulate is true. The first one we're going to talk about is alternate interior angles. A pair of alternate interior angles are going to look like two angles that are on alternate sides of the transversal, so left and right, or right and left, etc., whichever one you're discussing. And then interior refers to the parallel lines. Our parallel lines are this way right now. Interior means angles inside. So our pairs of alternate interior angles we're talking about are angles 3 and 6. They're on opposite sides inside, and 4 and 5. And what we're going to talk about now is like what's true about those angles. Well, let's go back to corresponding angles for a second. I know that angle 3 and angle 7 must be congruent because of corresponding angles that we just previously discussed. These angles, because the lines are parallel, they must be the same because they're pointing our lines in the same direction. We knew from before, our previous angle pairs part of the unit, that angle 6 and 7 also have to be congruent because they are vertical angles, right? Anytime a pair of lines intersect, resulting opposite angles have to be the same. So now we have angle 3 is the same as angle 7. Angle 7 and 6 are the same. Well, that means that angle 3 and angle 6 have to be the same measure as well as a result. And we can reproduce this in a variety of different ways. We could have reproduced this for 4 and 5 using different vertical angles as well. The resulting angles, then, measure angle 3, would have to be equal to the measure of angle 6. Well, 4 and 5 are also inside the parallel lines. They're on opposite sides. So these would also be alternate interior angles, and they would be equal in measure too. So what we just established here is because of corresponding angles and vertical angles, the alternate interior angles on a transversal with parallel lines are the same measure as well, and we could set up equations as such. Okay, well, if we have alternate interior angles, then we certainly have alternate exterior angles as well. We don't have to only deal with angles inside of the parallel lines. What about angles on the outside of the parallel lines? So let's take those for example. Opposite sides of the parallel line of the transversal, 2 and 7, 1 and 8, outside of the parallel lines. Imagine this set of parallel lines being a football field. These angles are out of bounds, exterior, out of bounds. So 2 and 7 would be considered the alternate exterior relationship we're about to discuss, 1 and 8. So let's talk about what that relationship is, although I have a feeling that many of you realize that this is going to be related to the alternate interior relationship. Let's look at 2 and 6. We know that 2 and 6 are corresponding angles because they're in the same position in the groups of 4. We also know that 6 and 7, as we just mentioned in the previous spot, are equal measure because of vertical angles. Well, if 6 is equal to 7 and 2 is equal to 6, that means 2 and 7 are both equal to 6. That means that measure of angle 2 has to equal the measure of angle 7. And we can expand upon that. The same is going to be true about 1 and 8 if we connect them using perhaps angle 4. The measure of angle 1 would have to equal the measure of angle 8. We would call these alternate exterior angles, and they are also equal. So we talked about alternate interior and exterior angles and the relationship that exists with angles that are on opposite sides of a transversal and then inside the parallel lines or outside the parallel lines. Those angles happen to be equal to each other in measure. So what happens now if we think about interior and exterior but on the same side of the transversal? So what we're going to do in this quick clip is we're going to talk about same side interior and exterior angles. We're going to cover them together because they end up having the same relationship. So let's take, for example, angles 4 and 6. If you were to describe them using those words, you would say that they are certainly interior. They're inside these parallel lines we have here. But they're on the same side of the transversal. They're both on the right side. So let's talk about angle 4 and 6 with a relationship we already know. We know that angle 4 is equal in measure with angle 8 because of corresponding angles. Another relationship we discussed in the previous part of the unit were linear pairs. Two angles that lie on the same line, their measure sums to 180 because they take up all 180 degrees of that straight angle. I'm going to use two markings here to differentiate because these are certainly not necessarily the same. They could be, but they're not necessarily the same. Angle 6 and 8, we know that their sum equals 180. So another fair equation here would be to say that the measure of angle 6 plus the measure of angle 8 would equal 180 degrees. We've built that equation a few times with our angle relationships already, just like we built the equal one with vertical angles. Well, if you take a look at my equations here, if the measure of angle 4 equals the measure of angle 8, we could just kind of sub that in here because they're the same thing. So I'm going to go ahead and do that now. We use substitution during systems, and I'm going to plug this measure of 4 right here where that 8 is, and I'm going to come up with a new equation. The measure of angle 4 plus the measure of angle 6 equals 180. I'm going to box that in for you here because what we've just done is we've used two certainly true statements based on relationships we've already accepted, and we've created a new equation that represents a new relationship that we're going to now just assume is true. 4 plus 6 would have to equal 180 degrees. They have to be supplementary angles. The same would be true for 3 and 5. And then consequently, the same would also be true for angles like 1 and 7 using the same way to prove it. we would prove by using 1 and 5 as corresponding angles and then 5 and 7 as a linear pair that the measure of angle 1 plus the measure of angle 7, would have to sum to 180 as well. This would be our same side exterior angles outside of the parallel lines, while 4 and 6, or 3 and 5, would be same side interior angles. The same side relationships will always be supplementary. They sum to 180 degrees, while the alternate relationships we talked about previously, well, they're equal to each other in measure. They're congruent.